All right, hello and welcome to the next week of lectures. This time, we're going to talk about something called containers, which I think if you just go back to the English definition of the word container, it will make sense. They're holding things. But first, let's talk about the final and then also some extra credit. And an extra credit opportunity. How about that? Okay. So, I'm eventually going to make this module, week 18, available. And that's where the final is going to be eventually. But right now I have final info and then the extra credit assignment. Okay, so let's talk about these things. So for the final, like I said at the very beginning of this semester, the final is going to be on the Tuesday of finals week. So I'm going to release it then on the 8th at noon. So the 8th of December is the Tuesday of finals week. And then I'm going to let that final be available up until the next day at 2 p.m. Okay, so December 9th is the Wednesday. Okay, so just make sure to start at noon on the 9th if you want the full time, because this is going to be a 2-hour exam. Okay, that's the amount of time that I will give you. And technically at this college, you're supposed to get 1 hour and 50 minutes to take a final, but I mean, this is the internet, so why not give you 10 extra minutes to do it? So I'm going to write a final from the point of view that you're like taking 1 hour and 50-minute final. So I'm not going to give you 10 minutes of extra questions. I'm going to give you 10 minutes of extra time. Okay, so that's that. And then let's just get into the topics. Not a lot to say because all of the topics in this class have built on top of each other. So the final will definitely be cumulative. I am sorry about that. That's just the way it has to go. And yeah, so it's just going to be taken from everything. I will try to, I can't promise that I will, but I'm going to try and give a bit more weight to the topics that we covered after the second midterm, but there might just not be enough material to do that with. So just expect a little bit of everything. Okay, so be familiar with all the stuff from midterm 1 and midterm 2, and then all the stuff afterwards. So like recursion, exceptions, searching, makefiles, bitwise operations. So definitely hit hard all of those topics. And then everything that I'm going to cover after those topics, like starting today with containers, you should still expect me to ask you some small questions about them, but they will be like easy. They will be quick. They won't be the majority of the exam. Okay, so that's all I wanted to say there. So these will be the definite topics that you can definitely expect questions on in detail. Okay. And just as usual, it's going to have multiple choice questions, and then the rest is like free response, fill in the blanks, coding questions. But the multiple choice questions I'm going to take from the remaining chapters in the textbook. So like the ones that I haven't tested you on yet. And there aren't a lot of those left with topics that I've covered in lecture. So there might be less or fewer multiple choice questions than usual. Just prepare for that, okay? I'll definitely still give some. Yeah, that's everything I want to talk about for the final. Please yell at me if you have any questions about that. And then let's get into the extra credit opportunity. So this one is going to be due the very last day of instruction. So that is the Friday, December 4th at midnight, or 11:59 p.m. And this one's going to be up to 5% extra credit. So use it if you need to. I encourage you to do this extra credit, and what you're going to do, just like the last opportunity, was to make a video reviewing concepts that will appear on the final. So maybe make a little PowerPoint, or like start coding stuff, put it somewhere and submit a link to it. This is going to be a discussion so your peers can see what you post, and they will love you forever because you are giving them help as they are reviewing for the final. So definitely consider doing this. Everyone will love you. And if you have any questions about how you might record yourself, or you have any difficulties with that, please talk to me, because I can either give you like an alternative assignment if need be, or I can help you get a laptop from the school that has everything you need to record yourself. Okay? I want to make sure that you can do this extra credit assignment if you want to do it. So we will find a way for you. Okay, so if you are going to do the video, please make up a bunch of examples, and they should be like not super easy, like stuff to prepare for an exam with. And don't just copy stuff that I've done in class. Like, don't copy my exact lecture and my exact examples. Be creative and do something new. Like, cover the same topics, but don't like redo everything that I did already. Like, have a cool new example and a cool new use case. Yeah, that's the idea for that. And then, yeah, just pretend you're giving a lecture, demonstrate everything you're doing, explain it like you're a teacher. And so if you want the full 5%, you have to make a review video that is at least 40 minutes long, okay? And I promise you that's not a ton of time. I've gotten a lot of practice making long videos this semester, and you can ramble on for 40 minutes without too much trouble. So give it a shot if you would like. And if you want 2.5% extra credit, do half the time, 20-minute video, and then half of that, make a 10-minute video to get a little bit of extra credit. Okay, so please consider doing this, and that is where I want to leave us now. Go to the C++ documentation now to get us ready for what we're about to do. So let's get started with containers, and we are going to store some stuff because that's what containers do. I can't remember if I already posted this meme somewhere on slides, but we're about to talk about these things called iterators today, so this is perfectly accurate to what you're about to learn. So let's get started. Let's have some definitions at the beginning. So the first thing that I want to talk about is an abstract data type, ADT for short. Okay? Maybe I should put that up here. And an ADT, as Wikipedia defines it, it's a class of objects whose logical behavior is defined by a set of values and a set of operations. So in normal English, that means I want you to imagine that a type, usually it's a C++ class that defines a type, right? Imagine that a C++ class is just a black box. You can ask it to do things by sending it messages. You can respond to operations. But you don't know how it's implemented. You don't know / care about how it's implemented. So from your point of view, let's talk about this like a vector, for example. A C++ vector, we have been imagining it's kind of like an array, but it's really not. So it really is a black box. And so here's your vector v. You declare it, and it exists, like here's v, and you can ask it to do things like, hey, please push back 42. And it can tell you, like, yeah, you got it. And we imagine that it has an array inside of it somewhere, like it's storing things, but we're not so sure. It doesn't actually matter, and it doesn't have to be using an array. In fact, as long as pushback works the way we want it to, as long as like @ works the way we want it to, and then it gives us back 42 because that's where we put it, right? As long as it like follows the model of being a vector, like it responds to the right questions with the right answers, for all intents and purposes, you can make your own little vector class that like stores its stuff in a very weird way. So a vector is just something that has operations that we associate with a vector. Okay, so vectors, for example, are black boxes that respond to pushback, popback, @ size, things like that. And if you make a class that works like this, that responds to these messages in the right way, you can make your own version of a vector. Okay, so that's what an abstract data type means. It's abstract. We don't know how it's implemented. It could be using an array. It could just be like putting everything into a very long string separated by commas. We don't care. as long as it gives us back the answers that we expect. Okay, so a container now is just any type that holds elements. Those elements can be of any type as well. So you can have containers that themselves hold containers. And for example, vectors are containers. And we can ask vectors to eat themselves and be like, you can make vectors with vectors inside, of course. So it's just turtles all the way down. Okay, so that is containers, and we're going to talk about those in detail today. Every container in C++, I want you to think about abstractly, like it's some black box that responds to commands, but those commands are very useful and they work in certain ways, and we'll talk about the trade-offs for each container. And in full, we call them container classes. Okay, so that's the motivation. That's the idea. Let's get on into it and start with something we know. Let's start with vectors. So remember that a vector. Well, what do you know? It's in the containers section of the C++.com website. It's as if these words that I'm saying, other people use them. Okay, so a vector works like this. Like it responds to all these messages that we can ask it to respond to. It knows its size, it can be resized, it can get elements at a certain index. So vectors are what's known as a random access container. You can think about the stuff that you put inside of a vector as existing at a certain index. And this is not true for every container, so it's very special for vectors to have this opportunity for you to ask, hey, what's at index 2? So it knows those things. Okay, so that is the idea for vectors, and we've already talked about the stuff that they respond to. But let me give you a hint for CSCI 41 when you eventually take that. Let's talk about how fast it is to do these things. Let's see if the documentation says it anywhere at all. Pushback, maybe? Let's see. Complexity. Aha. So the word complexity means how fast is this operation to do in time, and constant is the best possible complexity, if you'd like to know. Remember that. And several vector operations are constant time. Which is beautiful. Actually, there's a really nice website that I'd like to pull up for you, so I'll be right back. Okay, this thing's really cool. You don't have to worry about what this means, but O of 1 means constant time, O of log of n means logarithmic time, O of n means linear time, things like that. And we like it when it's constant or logarithmic. Everything else, it takes time now. So think of a vector as, technically, I think we can talk about it like an array. It's very fast to do many things inside of an array. So you can access things very quickly, like .at is constant time. .size is constant. Things like that for vectors. Some of this stuff doesn't even have that information. Search can be fast if you do binary search. Insertion is actually constant time for a vector. This is an array that it's talking about, so it doesn't know what it's talking about. Deletion in some cases is constant time for vectors, but eventually we'll be talking about lists and the trade-offs. So vectors can do a lot of things very quickly, okay? And moving around a vector you can use .at and like give indices. I guess you could use .at and .size to make sure you don't go off the end. And we think of vectors like not as black boxes, but technically as arrays that can possibly grow. Okay, that's what a vector is. It's a random access container that can grow at the end very easily. So it's very constant time to do these things. .add is constant, .size is constant, .pushback is in fact constant, which is all really, really nice. And so normally you've used like indices, like or pointers, like, okay, I'm looking at index I, which is now currently 1, so I'm looking at this thing. I want to do stuff with the 2, for example. And that's vectors that you know and love so far. But there's more. There's more to it. Vectors have these things called iterators. And all of these other containers also have these things called iterators. So let's talk about those. So these are all the things, these are all the kinds of iterators that vectors know about and can give you back. I'll really be talking about begin and end only for this lecture. But there are others, like you can have reverse iterators, const iterators, things like that. But let me show you. So an iterator is an abstraction over the concept of iteration. So let me show you 2 different ways to iterate through a vector. So you can iterate using like iteration variables, storing like the index where you're currently looking, index. So that's one thing that you can do. Alternatively, you can use iterators. This thing that I'm about to explain. And so let me show you the difference between the two. And there's actually 2 ways to use iterators in C++. You can do the full thing with what I'm about to show you, or you can use the range-based for loop that you already know about. That's really using this thing called iterators. So let me make this make sense now. So let me show you 2 different ways of iterating through a vector. Actually, I'll show you 3, but the last 2 are technically going to be equivalent. Okay, so let's get some vectors going. So vector int v equals 1, 2, 3. So I've made myself a vector. I can potentially add things to it if I wanted to, but here's option 1, non-iterator way of iterating through v. So that is just the normal thing. For int I equals 0, I is less than v.size, I++ or plus I, and then you can be like, okay, what are you doing with this? I don't know, cout v at I, space maybe, and then we'll give a new line. So that's the non-iterator way. Iterator way option 1, which you already know is the range-based for loop, and that is for int x in v, get each x out and one at a time in order, and take each element, call it x. So the first time the loop iterates, x is set to 1, the second time it's set to 2, the third time it's set to 3, and I could just do cout x, and then a space, and then a new line as usual. So that's actually using iterators secretly. So this secretly uses iterators. And now let me show you the cool thing to do after I run this. C++17. So just to prove to you, it does the same thing. But now there's one more piece of the puzzle. We have this. We have begin and end. So this is what it looks like. The type of an iterator is the class that it's an iterator on, so a vector of an int for our case, and then we say : iterator. It's like a type inside of a type, and that is what an iterator means. And you can think of .begin as a pointer to the beginning of the vector, so an iterator to the beginning. An iterator to the beginning of the vector, v in our case, and the type of v.begin for the vector in my example is vector int : iterator. Most people usually use auto because they don't want to type this out, but this is the full type. It's a type within a type. It's an iterator on vector of int, so it's this iterator is defined inside of the vector int type, which is weird. That's okay. That's what v.begin means, and then v.end is an iterator to one past the end of the vector v, which is weird to think about, but don't worry, I'm going to show you why that's important. And I want you to think of these iterators as pointers, because they are modeled after pointers and they kind of work like pointers. So for example, if I had v, which was 1, 2, 3, somehow v.begin gives me some type of pointer thing. To the first element. And v.end somehow gives me a pointer-like thing to one past the last element. So you never actually want to dereference v.end. Okay, so if you're not thoroughly confused, let me give an example of this working now. So can I show you the documentation for iterators themselves? Yes. So I'm going to come back to this, but let me show you the original iterator way. Option 1 was not available back in the day. Everybody had to do this. Here, I'll just say manual iterators. Okay, so we say for vector int iterator, give it a name, I call it IT, that's what I was taught, equals, so you start this iterator at the beginning, v.begin, then there's no less than anymore, you say IT is not equal to v.end, you don't want it to get to end because that would be past the end, we don't like that, and then you can say IT++. Technically, you should use ++ IT, but that's okay for now. Not a big deal. Okay. So, I have my iterators. IT starts at the beginning of the vector. I'm advancing IT using IT++ up there until it gets to one past the end of v. At that point, I want to stop this iteration. I don't want to use IT anymore if it gets past the end of the vector. And then inside of the body now, I can pretend that IT is a pointer to the current element. Okay, so you can think of it as a pointer, and now I can go to this. So what can you do to these things? You can pretend to dereference it. The star operator is implemented for iterators. You can say that. It works. You can go forward and backwards. You can say plus plus or minus minus. It'll all work out. Technically, you can compare it with inequality for interesting reasons, but that's the idea. So we're just going to use the plus pluses and the star in this example. So now, in order to output my current element, I can say cout star it, use it like a pointer, new line. Oops, then I want a space, didn't I? So, drum roll please, it does the exact same thing. And now the fun part is, in fact, this code right here gets secretly translated into this, okay? Option 1, secretly, gets translated into this code. So now you understand why it's working. It's secretly using these things called iterators, which are pretending to be pointers to things. And so let me show you what's going on here with IT. We had 1, 2, 3. Oops. And we started IT at the beginning of the vector. So it was kind of like a pointer. You can think of it like a pointer, but it's not. It's a special class. And then we advanced it with IT++. And so that moves it to here, plus plus again, moves it one more time. It just knows how to go forward. And then plus plus one more time starts pointing right after the end, one past the end, which is equal to, at this point, IT is equal to v.end. So v.end knows where one past the end is in its little encoding of where it is inside of the iterator. And at that point, we can stop the loop and be like, okay, we're done. We got no more valid indices to look through. Okay, which is all fun. And you might now be wondering, why in the world do I want to go through this much trouble to do anything? Like, why can't I just use my for loop? Why can't I use option 0 for the rest of my life and be happy? And the answer is, this way scales to other containers. Iterators work on other containers in the same exact way. So, just to reiterate that, oh, no pun intended, they scale, they work the same. For vastly different containers. And let me show you the next container. It's slightly similar to a vector, but not quite. So this is called a list, okay? So you have learned a little bit about this by reading about it in your book, and I showed you a very quick example. Even did a Xylab about it. So a list is an abstract data type that wraps around this linked list that you know about. But they don't have to. So let's go and take a look at these. Lists respond to, go to containers, list. The list class responds to similar things like size, empty, hey, is it empty? Oh man, does it have iterators? Push back, push front, pop front. Ooh, that's nice. Those are beautiful. Insert, erase, clear. Normally you use push front, pop front, and push back, pop back. Those are useful. And erase is also useful. So it's very similar to a to a vector, but you can't do anything like .at. That doesn't make sense in a list because you have to follow the list. All right, so this is what 1, 2, 3 looks like as a list. If this is like your list L, it's kind of like a pointer to this thing, 1, 2, 3, and you got to follow pointers to get to other places. And so this is what a list 1, 2, 3 looks like. You got to like go through 1 to get to 2 to get to 3. That's the idea. So think of it as a black box though that responds to questions like, hey, responds to commands. Like, let's say, push back, pop back, push front, pop front, size, etc. And lists are different from vectors in that they can do different things faster. So for lists, and I'll use singly linked lists, or let's use doubly linked lists as our example because that's what C++ is using. It is just as hard to search. You got to go through like every node if you want to do linear search, but insertion and deletion are constant. Ooh, is that nice? Ooh, is that nice? That is not something we had with vectors. To the front or back are constant. That is a trade-off that you can make by using a list. If you want to go in the front or the back of a list and put things there or remove things of like a container, you don't want to use a vector. You want to use a list instead. That's super nice, super fast. Okay, so that's what a list is, and let me build a list for you. So instead of including vector, I'll include list. And instead of vector, int v, I'll say list. I'll say list int l. Okay? So what you do to build up a list, it starts out empty. You can push back or push front in constant time. So I can say, let's do it in reverse then. Let's push front. Push front 3, then 2, then 1. Isn't that fun? So now the list holds 1, 2, 3 in that order. Isn't that fun? So that is our list, and we can do cool things with it. One thing that we can do is iterate through it. Oh man, list iterators work in the exact same way, even though there's no like .at. So they are the beautiful thing that you can always use in a C++ container. You can always go for the iterators. All right, so if you wanted to, the range-based for loop works again as well. Even though there's no .at, you couldn't have done option 1. Doesn't exist for lists. Range-based for loops work just fine. Int x in L, cout x, space. New line. It's all so wonderful. Bam, 1, 2, 3. And then we can do the the list iterator version, the full version. We'll say for start an iterator at the beginning of the list. So we have list of int iterator it equals l.begin. You want it to keep going as long as it's not 1 past the end, which is l.end. That always .end always means 1 past the end. it++. Cout star it space. Again, it does the same thing. Bam. Isn't this fun? So this is really exciting because suddenly iterators they just wrap around ideas. The idea of iterating through something. Like, here's my list L. Maybe in memory it looks like this somehow. Doesn't have to. But usually it does. And then I can start my IT like it knows what lists look like. And it can go and point to the beginning, the first node. IT++ knows how to move it from there to there. It doesn't look like a vector anymore. It's not all next to each other. It's following pointers deep down. But IT++ knows how to get to the next thing. And eventually it knows how to know when it's done, like it's got to the end of the list. So that is, at that point, IT is equal to L.end, one past the end. So iterators will save your life. They always work. Okay. Yeah, they work. You can also do minus minus. If you want to go backwards. So usually you should use reverse iterators if you wanted to do this, but let's try this. Let's be like, well, if that's one past the end, let's go to the end then. Yeah, surely that works, right? It's unequal to, so now we need to do something different about this, because eventually it'll get to the beginning. So that won't work. So use reverse iterators, please. But I'm just proving a point. So we don't want it to be equal to begin. Eventually we want to stop it. So this won't even work because it won't hit the beginning thing. So let's just say true. And we'll break if IT is equal to L.begin. We can break out of the loop after we visit the beginning. So in theory, this goes backwards. Bam. 3, 3, 2, 1. Not quite, but it kind of does. Oh, I actually know what the problem is. It wasn't end minus minus, because that gives back the old value. We want minus minus end. Do it first. Haha. Bam, now it's in reverse. So that totally works. The better way to do that is using reverse iterators. That's the more sane way to do this. There it goes. It will let me go over. Dun dun dun. So if I go back, reverse iterators, they look like this. You can go R.begin, R.end, so reversed beginning. You want to start at the R.begin and go up until you go one past the R.end. Like, you go until the R.end. That's the idea. So it's list of int reverse iterator. RIT. Yeah? Dun dun dun. I had some friends who went to RIT. Let's see here. Let's see how we want to do this. So, here we go. For list int reverse iterator RIT equals L.R.begin. Now we can do the normal thing. RIT is not equal to L.R.end. RIT++. Now we can say the normal stuff. Paste. New line. Oops, sorry, this is supposed to be RIT. And again, it works. So technically you can go backwards using normal iterators, though. That's probably a bad example to give, though, for doing it. Okay, so that's lists. They have some trade-offs. So there are trade-offs between lists and vectors. based on the kinds of things that they can do fast. Now I have two more examples, and the first is called set. So let's go there now. There are more than what I've talked about. There's unordered map and unordered set, but those will be saved for CSCI 41. So set, there's also a multi-set, if you want to read about that, but set is a container that stores unique elements in order, in a certain order. Standard set of some type T stores T's, like they could be ints, they could be doubles, they could be vectors, they could be other sets, whatever type T you want to pick, want to put in there. It stores T's, stores unique T's, and it also follows a given order. So just by default, you get orderedness, which is super nice. So think of a set as just like a big cloud, and you can put stuff in and get stuff out. Usually that's what you want to do. Put stuff in and get stuff out. You can say set of int, I don't know, s. You can say, hey s, please add one new thing, and the adding is done by the insert function. You can say insert, please, a certain number. Okay, so it's just insert a single element like that. You can say s.insert 2, and so it'll put 2 in there. And then you can say, hey, s is that thing in there. So insert, there's a lookup command, which is check if the thing's there, and it will be either find or count, one of the two. We'll use count. So insert count, and you can get rid of things. So like remove if it's there, erase. So it responds to commands like that, and the really nice thing about these commands that it responds to, if we look at the complexity of, like, I don't know, insert, in any order, insert, the complexity is logarithmic in general. You can disregard this last bit. Pretend it's logarithmic, which is very nice. So we're going to, let's see, which of these? Think of it like a red-black tree. I know I haven't used those words before, but that's essentially what it is deep inside. And all of the operations on it are logarithmic, which is, I mean, worse, slightly worse than constant, but not as bad as linear, whereas lists were linear to do quite a few things, linear to access and search. Arrays and vectors were hard to delete in certain places, but sets, which are encoded using red-black trees, we can assume, are logarithmic in all these different kinds of operations, and that's really nice. This is really fast. Okay, and oops, I was going to say s.count. Hey, how many 2s are there in there? And if it gives back 1, if it gives back a non-zero value, it's going to be like, oh yes, it's there. So let me show you set. And or I'll get us started with set, and we'll probably have to come back next time. Because we are running out of time a little bit. Let's set, I can say set of ints s, and I can insert things. s.insert 1, or I can do it out of order just to prove a point. 213. So that's inserting, and then I can check if it's there. In logarithmic time, super fast to do so, I can say, all right, hey, is 2 somewhere in this set? Say s.count 2. Is there something there? And it will give us back the number of things in the set. And remember, it's unique, so it's only ever 0 or 1. It's going to be 1 because it's there. And if we ask for like 4, which doesn't exist, it'll tell you very quickly that it's not there. So that's where I want to leave us for now. In the next lecture, we'll come back to sets and we'll talk a bit more about them because there is more under the hood and there's also an iterator involved. So I'll see you in the next lecture.